Bonjour, Alexandra Gillespie and Adishnikos. I greet you today from the campus of the University of Toronto, Mississauga, where I live. The window next to me looks out over Missinaihi, the river that the French and British called the Credit, because at its mouth they traded with Indigenous peoples, who for thousands of years had travelled and stewarded its waters and the lands around it. I and my collaborator, Dr. James Sargan, a Leverhulme postdoctoral fellow at U of T, an expert on early Middle English manuscripts and reading practices, and our lab specialist on the use of MicroCT for codicological study. We present this research to you from the traditional lands of the Wendat and the Seneca, and the territory of the Mississaugas of the Credit First Nation. We acknowledge this and the guidance of the Mississaugas of the Credit, the friendship they show to U of T's communities, as well as to those we work with locally and internationally as we seek to be good kin and to live a good life. Chimagwech. Today's paper is drawn from the results of a 2-year collaborative Mellon-funded project, The Book and the Silk Roads is its name. At its broadest level, our project sets out to confront a persistent Eurocentric myth about text technology. The idea that only in the West did books advance civilization because no non-Western culture could match the achievements of the Roman alphabet, the Christian codex, or Gutenberg's printing press. Our project, which depends on a broad and deep network of collaborators from across different humanistic disciplines, approaches a wide spectrum of books from around the world, focusing on evidence of international development, entanglement, and convergence over fictions of inferiority. Our project is designed not only for this sort of bibliodiversity, but also for multidisciplinarity. It brings together historians, paleographers, philologists, literary scholars, and librarians with external collaborators from the sciences, including the conservation sciences. We are working, among other projects, on proteomic evidence of parchment species in Ethiopian gospel books from the Horn of Africa, these on deposit at the Art Gallery of Ontario, on patterns of lipid and other stains on single leaf printed books from the Dunhuang caves of Central Asia, one of which is at the Royal Ontario Museum, and on what MicroCT can reveal about the sewing structure and other internal binding structures of a Kashmiri codex in the Fisher Library in Toronto, in which Sanskrit manuscript text is laid out in a Persicate book form. At the Copenhagen Care and Conservation of Manuscripts Conference, we know we're in distinguished company when we say that our work encompasses the materials and structures of the book, as well as the texts and images the book contains. But our focus on the manuscript's three-dimensional form, as well as its content, does something particular for our project. It supplements humanistic work within, but also orients humanistic work beyond the ethno-national, religious, or linguistic categories which usually organize that work, and which developed from the colonial practices and national philologies of the 19th century that gave rise to humanities disciplines. New scientific approaches enable us to mobilize the book, not just as a source of knowledge about Sanskrit texts or scripts, or Islamic religious practices, or European history, but as a source of many forms of knowledge, grounded in local conditions, but contributing to a richer, more various story of the human and non-human global past. Our paper today will be about just one new scientific approach, microcomputed tomography for imaging books. New here means recent and evolving rather than novel. Many of you will know about the important work done to image the British Library's St. Cuthbert's Gospel using CT technology. MicroCT has been crucial to a variety of projects to recover texts from damaged, unopenable books, where those texts have been copied in inks containing metallic compounds, so that CT can reveal them and they can be read. And here we think of, for example, Brent Seale's and others' work on the Engedi scroll. We have, as well as many other books, we've sought to advance the CT technique as we build local capacity for MicroCT work, and also to focus our project, to focus this work on our project and our collaborators' particular research questions on books' constituent materials, concealed structures, and layers of accretions. I'm now going to hand over to Dr. Sargan, who will talk about our progress.
Hi. So when we submitted our abstract, I had anticipated having several manuscripts from different places, recently scanned, ready to talk to you about comparatively. But like everyone, our plans had to change. So instead, I want to walk you through a more detailed look at the proof of concept scan we did before the pandemic, thinking especially about what kinds of things MicroCTs like this can tell us about book bindings. And then I'll come back to the Kashmiri book that Alex mentioned. The manuscript we scanned for this proof of concept work is a late 15th century Book of Hours, that is, an abbreviated form of the Catholic liturgy to be used in personal devotion. The book is held by Western Life University in London, Ontario, who are our partners in this scan. There we worked with Debbie Meert-Williston, the Special Collections and Rare Books librarian, and Andrew Nelson, chair of the Department of Archaeology and Anthropology. We approached them to collaborate with us on this project because of the special combination of expertise they offer. Debbie is a former forensic pathologist, and Andrew's primary research focuses on non-destructive imaging of mummy bundles. So both of them have a special interest in approaching books from this anatomical, bioarchaeological perspective. We knew Andrew especially for the work he had done MicroCT scanning medieval boxwood prayer beads for an international exhibition that ran at the Art Gallery of Ontario in Toronto from 2016 to 2017. Our manuscript was copied in French Flanders, probably in or around the city of Lille. The personal nature of the book points to one of the reasons that we chose it for our first scan. Because it's meant for individual study, it's small, palm-sized. When it's closed, it's only 13 centimeters tall and 9 centimeters wide. So it fits fairly easily into the small scanners we use, and we could image it at a fairly high resolution with just one scan. Bigger books are more labor-intensive because we have to take multiple scans that then need to be digitally stitched together. Another reason is this book's binding. The manuscript was rebound in the 18th century. It is covered in a fairly low quality, undecorated brown leather, which is wearing through at the edges of the boards. The spine profile indicated that it's sewn onto 3 raised supports. To all intents and purposes, then, it conforms to Nicholas Pickwode's description of inexpensive commercial designs of the time. That meant the book was familiar enough to us as people trained on Western European manuscripts that we felt fairly confident about what we expected to find when we imaged it, which would allow us to assess the capabilities of the technique and consider how we might apply it to other, less familiar objects. Now, many of you may be familiar with microcomputed X-ray tomography as an imaging technique. There are several papers at this conference presenting work that uses it. Most significantly for our purposes, it has been used by research teams to read lost or hidden texts, items that can't be opened due to their fragility, like the Herculaneum papyri, which were so carbonized they could not be unrolled until Vito Micella and his team used the synchrotron CT to do it virtually. For that reason, I'll just explain the principles of our method briefly now, but we can come back to it in the questions later if anyone wants. Andrew Nelson scanned our manuscript using the MicroCT scanner housed at the Museum of Archaeology in London, Ontario. To do that, he placed the book in a foam mount which holds it upright. In the CT scanner, a radioactive source emits a narrow beam of X-rays through the book and onto a high-resolution detector behind it. Andrew uses a molybdenum target, which maximizes the contrast in the scan. We made 2 scans, one at a resolution of 80 micrometer per voxel and another at 40 micrometers per voxel. Inside MicroCT scanners, either the object or the X-ray source and detector is rotated. In this case, it's the source and the detector. That way, rather than a single flat X-ray, like the images you might get after breaking your arm, the CT gathers and compiles many images which are combined to create a 3D rendering of the object. The results of this initial scan were thrilling. Unlike inside bodies, most of the materials inside books, parchment, paper, wood, thread, are very close in density. And there was no guarantee that each component would stand out from the others as clearly as they did on our first attempt. So beyond simply providing an image of the inside of the structure, going through the scan, it became clear that there were three major areas in the study of bookbinding that our results would impact. First, the identification of materials. What are they? How are they made? Second, the techniques at work, the mechanics of the binding. And third, and most exciting for our purposes, even in this book that we were confident we understood, it led to new discoveries. Some we were expecting, some we were not. So I'll start with number one. What material makes up this binding? Being an 18th century binding, we were expecting the boards to be some precursor of cardboard, but there were a few possibilities as to what. The binding has undergone some modern repairs, and it's not possible to learn much about the qualities of the board from the outside. So I'll just pull up my laser pointer. The cross-section of the board seen here makes visible the lamination characteristics of paste laminate board, or paste boards. As you all know, such boards are made by pasting together layers of often waste material. So when we scan them, we get this layered effect. And the cracks we find across the board confirm that ID. We only get fissures in this plane, not through the board at 90 degrees this way, which would have cut through the layered materials. So it's obviously much stronger in that direction. And we can say a bit more about how these boards were made. If we compare the thickness of the layers inside the board with the thickness of the parchment that makes up the book block, those in the pasteboard are markedly thinner. That, combined with the rippling of the edges of the fissures, suggests that they're paper, obviously, as we would expect for in a binding this age. Interestingly, though, if the paper in the boards was recycled waste, we might expect to see traces of ink left on it. Iron gall ink reflects X-rays extremely well due to its metallic components. But there isn't any immediately apparent evidence of this. Instead, what we get are these bright points included throughout the board. It might be that the paper used to make these boards was blank, and the pasteboard was purpose-made for commercial binders as part of the production process. Or, and perhaps someone in the audience will be able to confirm or deny this, could this be due to the method used to make the boards? If their manufacture involved soaking, but not pulping waste pages, and then drying them in layers in the manner of water leaf, then any remaining ink could have been washed off the surface and deposited more evenly throughout the material. What we do know is that often written material does survive in pasteboard, as well as in other places within bindings. And the fact that we can identify the individual layers of the board here suggests, with some work and by applying the same unwrapping and flattening techniques used last month to unfold sealed and locked letters, our colleagues in engineering and computer science may be able to help us read such recycled fragments without damaging the bindings that hold them. So in this next example, materials meet techniques. Here we have the sewing supports we could identify from external observation. And by zooming in like this, we can see that they're made of single lengths of fine cord. Digital measurements show us this cord is roughly 2 millimeters in diameter. And a look at the ends of the cords shows us their structure. So what we have are 4 2-ply strands, 2 with Z twists, 2 with an S twist, which are then only loosely twisted together. in terms of techniques, looking from a different angle, again, through the cross-section of the boards, we see how they're laced in. So here they pass around the outside of the board, in through this hole, along the inside, and out to the outside again. But the story is a little more complicated. From the frontal plane, face onto the board, we can see on the outside where the cords enter about 5 millimeters from the edge. They then run directly inwards on the inside for about 1 centimeter and emerge again. But then the cords are taken off at an angle between 55 and 75 degrees and go back through to the inside of the board where we get a knot and the frayed outer ends we saw earlier. So the great thing about MicroCT is that we have this volumetric medium that lets us examine the material from all angles and put together this holistic picture. From this view, we also get a clear picture of the all-along sewing. So here the thread is running up the inside of the gathering. It goes out, through and around the sewing support and comes back in through a different hole to run up to the next sewing support. Finally, our third thing, something new. What we were really hoping to see when we embarked on this scan was evidence of a previous binding structure. Looking at this shot of the spine, between the current supports here, we find a series of holes, 4 parallel rows to be precise. The holes pierce the center fold of each gathering, marking the now unused sewing stations from a previous binding. We've been calling this trace evidence of now lost structures a ghost binding. And by flattening the spine along the sewing path, we can observe a full set of holes in a single frame. In doing so, we see that each sewing support is made up of a set of 3 stitch holes. So you can see the major ones here, and then along the middle, an extra set. This pattern can only be explained if the gathering were attached to double supports using a 3-point stitch. Now, it's not like that method was particularly uncommon in the late 15th century when this manuscript was made, but it is more labor-intensive than other possibilities. 4 double supports are also a slightly larger material investment than the current 3. So this original binding was rather more elaborate, even if only in the details of its construction, than the current replacement. Now, there's a lot more that I could say about this scan and this seemingly innocuous 18th century binding. And I've put up this slide as a taster that we could come back to if there's time and interest in the discussion. But I want to move on briefly to give you a glance at the scan that Alex mentioned before I hand you back over. So this last manuscript, we scanned before the lab was closed, is a 17th to 19th century copy of the Bhagavad Gita from Kashmir. The manuscript belongs to the Thomas Fisher Rare Book and Manuscript Library here at the University of Toronto, and we scanned it in collaboration with Tim Perry, the curator there, and Giovanni Grasselli's geomechanics group, who are based in our engineering faculty. We're interested in this binding for its layered fabric cover, which includes a 3/4 envelope flap that wraps around the outside, as well as what seem to be interleaved images and how they're sewn in. What we found is that we could identify the layers of fabric and separate out at least 3 of them. They can be seen as cross-hatching in the frontal view here, so especially on this side. With more samples and careful measurements, I think it'll be possible to distinguish the colorful patterned inner from the looser weave outer. We can also identify the sewing patterns. There are at least two, and to me this looks like the images we saw tacked in using archive sewing around the outside of the gatherings, which are sewn down the middle. So here's the angled stitches around the outside and the sewing running up the middle. But this is where Alex's discussion of the collaborative global approaches to the history of the book comes through. One of the reasons we were so excited to have the opportunity to speak at this conference was to invite you to think through this scan with us, its materials, the sewing techniques, the attachment of the binding. The CT scan provides the raw materials that allow us to start that discussion. And I'll hand back to Alex to conclude our paper.
Thanks so much, Dr. Sargan. So I want to end by moving back and outwards from the specific technique, MicroCT, our experiments with it, and then our early uses of it for our project to a broader view. One of the many things that the COVID-19 pandemic has taken from us is access to embodied knowledge, to the evidence we gather, the ideas we glean, when we handle research materials in person, when we measure and feel books, when we hold their weight in our hands and even smell them. In doing so, the pandemic has intensified the priority that the digital era already affords the visual. We may not be able to visit our books or even meet with each other to talk about them, but we can at least see them as we can see each other. And right now, that's something worth hanging on to. Something valuable about MicroCT as a technique, however, is that it operates at the limits on that visual perspective. It provides access to details that the human eye cannot perceive. And as it does so, it reminds us that digitized manuscript archives, that right now are all that many manuscript scholars have to work with, offer only a surface, two-dimensional and logocentric perspective on the book. MicroCT, we think, offers all of the evidence you've just heard discussed. It also offers a compelling new way of seeing books. Like others in this space, we're working with computer scientists, we talk about that collaborative model, to find algorithmic solutions to some of the challenges the technology still presents, to flatten pages, to distinguish carbon inks, in which so much of the world's manuscript text is written, from the carbon substrates that text is written on. We're also compelled by how MicroCT can help us measure and model overlooked internal structures of books without dismembering them, without disbinding them or taking them apart. And of course, we're compelled by the way it gives us another tool for identifying by structure and density book materials, potentially wood species, textiles, papers, and pigments. For us, this is proof of concept for our project as a whole. It's an example that shows that methods drawn from the humanities, from curatorial studies, from conservation science and the natural sciences can be combined to reveal the human past in books and to illuminate books' record of human interactions with the non-human world. Thank you.